Matrix method of structure analysis. Now we are dealing basic introduction about matrix method of structure analysis, as we have discussed previously in the class. But once again we are going through the concept. So in matrix method we have two methods of analysis. One is flexibility matrix method and next one is stiffness matrix method. Actually we have different methods to analyze, but why we go for matrix method is normally every structure can be solved using different methods like slope deflection, moment distribution, Canis method, etc. But to design multi-structures with different multi-story buildings, the analysis becomes difficult using those methods. So that is why we use this flexibility matrix method and stiffness matrix method. So what is meant by why we are using this flexibility matrix method and stiffness matrix methods of analysis is to analyze the structure in an easy way. Okay, so to analyze the structures, how we are going to analyze the structures using flexibility matrix and stiffness matrix. So you can easily remember one thing, that in the stiffness matrix method, stiffness defines to K. Just for our remembrance, we can take it as stiffness is denoted by K, so that is kinematic indeterminacy. And whereas flexibility matrix method relates to the other one is, that is static indeterminacy. Okay, so here this is kinematic indeterminacy. So normally the structure, when it is indeterminate, we cannot solve this structure or analyze the structure. For that we are supposed to make the structure into determinate. Okay, and then to make it determinate we use this methods, that is flexibility matrix method and stiffness matrix method. So as we know that static indeterminacy deals with number of redundants and kinematic indeterminacy deals with number of degrees of freedom or number of free forces. Okay, so what we are analyzing in this flexibility matrix method is first we will find the number of redundants or degree of static indeterminacy, then release forces based on the redundancy. Redundancy is nothing but number of force which are restrained or constrained over there, or the forces which are existing additional than the equilibrium equations. Okay, so then we will find out those redundants, how many are there. After that, then calculate the moment in the members as per the loads. After that, then calculate the displacements based on the conjugate beam method for released members. Okay, we have redundants we have applied, or we have released some redundants, right? So these resultant redundants we are applying some displacement on them, and for that releasing load we are calculating the moment based on the loads whatever we have got. Okay, for this the shear is calculated, that is taken as M by EA. Okay, this M by EA represents the shear in conjugate beam. Okay, and next, to form flexibility matrix method, we will apply the unit load at each condition. If suppose let us consider beam which is simply supported. Okay, so one end it is fixed, the other end is hinged. So what is the static indeterminacy of this frame? There are 3 restraints with respect to fixed support and 2 restraints. Totally we have 5. Yes or no? So the equilibrium conditions are 3. So the redundancies or degree of static indeterminacy is 3 minus 2, that 5 minus 3, that is equals to 2. So this 2 is the degree of redundancy or static indeterminacy of the fluid. So to make this structure a statically determinate, what we will be doing, we can make this fixed support into a hinged support, so that one force will be released and it becomes 2, and we can make this hinged support into a roller support, okay, so that one force will be removed over here. So what are the possibilities to make the structure statically determinate is, first condition is making the support fixed to hinged and then hinged to roller. In this condition, the structure is stable as well as the structure is determinate, okay. So, and the next case is, either we can remove the two forces from the hinged end, that is from the other end we can remove these two forces, that is one is the vertical force, and next one is the horizontal force, okay. So here in this case it becomes a cantilever beam. Here also the structure is stable with respect to fixed end, okay. So what are the possibilities for which we can take the structure to make it determinate that we are supposed to think? Or else we have another option as well, that is making the fixed, totally removing the redundance from the fixed support and make it roller and then hinged. It is similar to as the first case, okay. These are the three possibilities for which we can make the structure as determinate. So in this case, what we have done, if we go for the first case, we have released the moment over here and then the horizontal force, okay. We have released the moment and the horizontal force. So two forces are released. These two redundant we'll be taking as the released forces of redundant. Based on this, we'll go for calculating the matrix method by applying the unit load with this released loads, okay. So if you go for applying a cantilever condition, then we have removed two forces, that is one is at fixed, one is the horizontal and one is the vertical at the second end, okay. So now I think you have understood how we are making the structure into statically determinate, okay. When we release these forces, obviously what happens is the structure, when some x force is released, we are supposed to consider the displacements or deflections taking place with respect to these released forces. So either it is static determinacy or kinematic determinacy, the analysis should be done for the released forces or added forces, okay. So for that case, as we have discussed in the point, we will form the flexibility matrix method and then we will apply unit forces wherever we have released the loads, okay. Wherever we have released the equilibrium conditions or resultant conditions, there we will apply the forces. After that, then we will calculate the matrix, that is delta I into J. So here what is I, what is J is, normally when we release these forces, that is the indeterminacy whatever we are getting or degree of redundancy is defined by the matrix. Always this matrix, that is matrix of delta I and J, will be a square matrix which is equivalent to the determinacy value, okay, indeterminacy value. So we got the value of 2. So the matrix forms a indeterminacy matrix, that is delta of 2 by 2. Clear? So this, yes. So after forming this matrix, then we will find out the displacements with respect to the matrices. So how do we form these displacements of the matrix? We will discuss now. So this is a matrix form, delta of P, delta matrix into P matrix into capital delta minus delta L, where P is a matrix for which we have released two forces, right? The values of these two forces we are going to find out using this matrix P, which are the unknown moments or forces which are released to form. And delta is the matrix which is considered as 0. This delta matrix comes into existence when you have a sway load or any displacement or sinking in the supports exists, then you will have with these values. So, or else if a sway load is acting on the frame, then the delta matrix is considered. And delta L is nothing but is in the step previously we have calculated delta L, that is the shear with respect to the conjugate beam based on the load, actual load applied in the frame, that we are considering, and the shear we have calculating, that shear load we are taking over here. It is delta 1L or delta 2L. If the matrix is of 3 by 3, then it have delta 3L as well, and the values are P1, P2 and P3. So if you have a degree of redundancy or static indeterminacy is 3, then the matrix will be formed as 3 by 3 matrix, and this will become as matrix P1, P2 and P3. So 1 by 3 matrix. Okay, and the delta matrix is, for example, if you have 2 by 2 matrix, then delta 1 1, delta 1 2, delta 2 1 and delta 2 2. If you have a 3 by 3 matrix, then delta 1 1, delta 1 2, delta 1 3, delta 2 1, delta 2 2 and delta 2 3 and delta 3 1, delta 3 2 and delta 3 3. So this is the matrix form of 3 by 3 if we have a static indeterminacy as 3. So what is delta 1 1, delta 1 2, delta 2 1, delta 2 2 is, suppose for the same beam we will take it as, see, this is our beam which is having a fixed support and a hinged support. For this we have released two forces, one is at A and one is at B. Okay, so one is at A and one is at B. So for these two forces, first force, if I am applying a unit load, that is, if I am applying a bending in this member, so obviously what happens, the structure goes for a deformation in this way. Am I right or not? So with this deformation we are supposed to, or the structure goes for a deflection. So due to this deflection, delta 1 1 is developed over here and delta 1 2. Okay, the displacement which is developed over here is delta 1 1 and delta 2 2 is over here. For example, as we have discussed, we are supposed to apply 1 kilonewton of loading condition. So at first we have applied a kilonewton of loading. This is the load diagram. If we apply 1 kilonewton of load at A, so what happens, the frame is formed as this one and the shearing with respect to the loading is 1 by EI. Okay, so here 1 kilonewton of load we have applied So what is the value? Here we are having the maximum value, and here the value is 0. This is the first case, and the value with respect to delta 1 1, that is due to the displacement at first displacement and first force. Okay, at the first force, what is the displacement due to the first displacement? That is first force we have applied. This is the displacement what we got, or the load diagram whatever we have got. So with respect to this, the first displacement, first force, and with respect to the first displacement, first force, there is a reaction at point B as well. So that is taken as first displacement, second force. In the second condition, due to the load application at B, the diagram is formed in this way. Okay, so here delta 21 comes over here. This is the second displacement which is occurred due to the application of load at B, and hence the delta 21 is second displacement, first force. Whatever the reaction happened at the point A, or the first force, due to the second displacement is considered as delta 21, whereas delta 22 is nothing but the second displacement with respect to the second force is considered over here. So by these values we will be taking out the matrix form, and then we will go for forming the matrix. After forming the matrix by using this formula of matrix, equation of matrix, you will go for finding out the values of P1 and P2. Okay, after that drawing the bending moment diagram. So for this being, normally other than the loads which are released, there may be a point load or UDL or UVL or etc loads. So these loads we are going to compare with respect to the whatever the loads we have got with respect to these releases, and then we will draw the bending moment diagram. This is how we go for analysis.